So welcome everybody. Today we've got Karin Howell from Stellenbosch, my own university, and we're very happy to have her. She's well known to the African mathematics community. She's a well-established and highly regarded researcher internationally in the field of near-vector spaces. She's supervised a number of honors, masters, and PhD students, with more on the way. She's also a great teacher of mathematics. She's taught AIMS courses at AIMS South Africa for many years. And she's been a long-time convener of our first-year mathematics modules at Stellenbosch. And she has won no less than 10 Vice Rectors Awards for excellence in teaching. She's also very active in promoting and supporting women in African mathematics, and is one of the organizers of the African Women in Mathematics virtual seminar. And she also was one of the organizers of the African Women in Mathematics conference, which was held in Stellenbosch 2019. So we thank you very much, Karin, for offering to speak, and we look forward to your talk.
Thank you, Bruce. Can you hear me?
Yes.
Okay, super. So I just want to thank the organizers, and in particular Bruce, for inviting me, and also thank all of you for coming. So my talk is entitled The Weird and Wonderful World of Vector Spaces, and I'm hoping to convince you of both their weird and wonderfulness. So I'm first just going to give you some background. I've decided to give the talk a slightly different feel. Since the definition is quite a lot to take in, I'm going to spend some time just explaining what it is and giving you some examples so that we get to grips with the material. And then I'll start going into some of the areas that I've been interested in. So hopefully I'll give you a flavor of near vector spaces and convince you that they're as weird and wonderful as I like to think. So I'm going to start with the definition. So firstly, I just want to say that this is not the only definition for a near vector space. So the idea with a near vector space is it's a structure that has a very similar structure to a vector space, but less linearity. And the less linearity is caused by the fact that one of the distributive laws is weakened. And depending which distributive law, you'll either have a right near vector space or a left near vector space. And then several authors have tried to capture this notion of what a near vector space should be. So Andre is the photo that you have on the page here. So most of the work that I have done is based on how he defined near vector spaces. He's well known in geometry, and he's done a lot of work in incidence geometry. And the way he defined his near vector space was motivated by his study of near affine spaces. So I'll talk a bit more about that later. In addition, I just want to mention that there is another notion of a near vector space that was first defined by Helmut Kozel, who unfortunately I learned passed away last week. But if you look up his work, you will also find a definition of a near vector space. And then there's also a near vector space defined by Badelman in his PhD thesis. And recently I co-supervised a student with Gareth Boxall at Stellenbosch University, Prudence Jagba, who studied these structures, and his thesis was on that topic. So Andre defined a near vector space as a pair where V is a group. So we have an additive structure, and then we have a set of endomorphisms of V. So that will be our set A. We're going to assume that A contains the endomorphism 0, the identity, and the inverse identity, which just sends every element to its inverse. And we also need that our non-zero elements of A form a subgroup of the automorphism group of V, which we know forms a group under composition. Next, we want to ensure that A acts fixed point free on V. You'll notice here that unlike normal convention for vector spaces, we will write the scalars on the right, and that's just because Andre did it initially, and because in our work we like making use of right near fields, so this is more natural to us. But if you put the scalars on the left, there would be no problem, and it might be easier for you to follow. So if x alpha is equal to x beta, where alpha and beta are scalars, then either x would be 0 or alpha would be equal to beta. And then the last axiom is a special axiom. We have this subset of V called the quasi-kernel of V. And the way I always introduce the quasi-kernel is that it's a set of elements that have some linearity. And they are very important because in the material, we will define a basis of a near vector space to be a linearly independent generating set of the quasi-kernel. So this is already quite different from vector spaces, where we would say that a vector space has a basis if there's a linearly independent generating set of V. Here we require a linearly independent generating set of the quasi-kernel, and the quasi-kernel in turn generates V additively. And that just means that every element of V can be written as a sum of elements of the quasi-kernel, or multiples of elements of the quasi-kernel. So I've included a picture of Andre on the right. He sadly passed away in 2011. We recently learned, my students and I have been trying to find out more of his work and more about him. And recently we discovered some very interesting papers written in English on his incidence geometry and how that work relates to near vector spaces. So it's a very exciting time to be studying these structures. A lot of things that we've been wondering about are becoming more and more clear with time. So we will refer to V as a near vector space over A. And the elements of V will be called vectors, just like we're used to, and the elements of A are going to be called scalars. So as a first example, I just like to give you an example of a vector space versus a near vector space. So obviously there's a lot of theory here that I'm not going to include in the talk, but if you're interested, I can refer you to some reading. But let's start off with a very simple set. Let's look at Z5. Then if I took 2 copies and I just use the multiplication, the normal multiplication to define the scalar multiplication, then we have a vector space structure. And we know quite a lot about that. 1, 0, 0, 1 would be a basis for it. On the right, I've done exactly the same thing. I've taken 2 copies of Z5, but I've defined the scalar multiplication as follows. And here you'll see I've written the scalar multiplication on the left, just to make it more accessible to you. If you haven't studied near vector spaces before, this often helps. So if you look carefully, what we've done here with the scalar multiplication is in the first coordinate, we're multiplying as we normally would. But in the second coordinate, there's a perturbation. And what we've done is we took a cubic power of the scalar and multiplied that by y. And that's enough for the structure no longer to be a vector space, but instead to be a near vector space. And you might wonder now which axiom is missing. And the axiom that will be missing is that we won't in general have that alpha plus beta of xy is equal to alpha xy plus beta xy. So that's the axiom that in general we will not have. I see I actually did write that there already. If we wanted to write down the quasi-kernel of this set, then all the elements that have a little bit of linearity, which is described here, for all alpha and beta in A, we can find a gamma in A such that x alpha plus x beta is x gamma. If we wanted to find this set, then we would see that it would consist of the union of these elements. Sorry, that should be in F. And so what we see now is that in this case, here's our V, and our quasi-kernel would be a proper subset of V. Now, with near structures, you ideally want your structure to be defined in such a way that what you regard as the near structure, so that it has less linearity, would include the actual structure. So what I mean by that is you may know of nearing theory, and nearings are rings where you're missing one of the distributive laws. Now, near vector spaces are a specialized subset of nearing theory, and there you have a right nearing or a left nearing, depending on which distributive law you have. But the way in which a near ring is defined includes that every ring would be a near ring. And in the same way here, in the very least, you want your near vector space to be defined in such a way that every vector space would be a near vector space. So if we think a bit about the vector space and how it's defined, then we will quite easily arrive at the conclusion that every vector space is a near vector space, and that here the quasi-kernel would turn out to be the whole space. So that's nice that we can draw a picture of the quasi-kernel being a proper subset, an example of that nature, whereas here in the vector space example, the quasi-kernel would be the whole space. So you might ask about basis. So I've already said that a basis is defined as we normally would want it, so linearly independent and generating. But for a near vector space, we need it for the quasi-kernel, and that will become a basis of V. Whereas for a vector space, we want a linearly independent generating set for V. But in this example, for both of them, the basis would be the same. Of course, the scalar multiplication is different. Run out of space here, so well, it's also a basis for this one here. All right, so if we go a bit deeper into the theory, regularity is very important for a near vector space. And just to tell you what the regular property is, it's the property that allows us to study vectors, near vector spaces in a way that is very similar to near vector spaces. So I'll explain in a moment. But we say that a near vector space is regular if for any two non-zero vectors of the quasi-kernel, we have that we can find a non-zero element of lambda such that U plus lambda V is in the quasi-kernel. So this is again some linearity that we have for some elements. And if we have that property for any two non-zero elements in the quasi-kernel, we will say that the near vector space is regular. Now, regular near vector spaces are called the building blocks of near vector space theory. And the reason is as a result of the decomposition theorem, which is one of the main results of Andre. And he proved that every near vector space is the direct sum of regular near vector spaces, such that every non-zero element of the quasi-kernel will lie in precisely one direct summand. And these subspaces would be maximal with regards to the property of being regular. So by studying the regular parts, we can always arrive at information about the near vector space, since the decomposition theorem ensures that every near vector space can be decomposed into regular parts. Now, regular near vector spaces so far in our studies have proven to be the closest to vector spaces, in that the properties that we have investigated indicate that they will have the same properties as vector spaces. So the most interesting investigations are what happens when a near vector space is non-regular. And again, if we think about our axioms for vector spaces, then it won't take us long to arrive at the conclusion that every vector space is regular. So it won't decompose, it will be its own decomposition. So not very interesting, but we can still see that there's regularity. Okay.
Karin, can I pause?
Yes.
There's a slight issue with the sound. I wonder if it's possible for you to, like, transfer the mics so that the mic, with that.
Let's try that.
Okay, how's that?
Let's go for a while and see how it goes.
Okay, that sound better?
I think so. I think it was just an issue with the recording, but I think it's fine now. Thank you.
Okay, super. Right, so if we return to our first example where we took two copies of Z5 and we perturbed the scalar multiplication, we've already seen what the quasi-kernel will be. And what the decomposition theorem in this case would do is, firstly, this near vector space as it stands is non-regular. And by applying the decomposition theorem, we get that the near vector space can be decomposed into two parts, and these are the two parts, and each one of these are regular. Okay, so without going into the detail of the decomposition theorem, how it works is you look at the quasi-kernel and you look for all the elements that are mutually compatible. And it just happens that when you look at constructions of copies of ZP over itself, then the parts that make up the union of the quasi-kernel will be exactly the maximal regular subspaces in the decomposition. Right, so that was an introduction to what I call the wonderful. I don't think I've quite convinced you yet that they're wonderful, but I'm getting there. But here's some weird. So this is work that was a collaborative project with Sulgu Sanon, who's now in Germany. I'm hoping that in the future he can make his way back to Stellenbosch University for us to continue with some of the questions that we would still like to answer. But span is a notion that's very well known in vector space theory. We know what a span of a set of vectors is. We know what properties we would normally have. So it was very natural to define this for near vector spaces and then try and see what carries over and what does not. So if we have a near vector space, then the span of a set of vectors is defined to be the intersection of all subspaces of V that contain S. It's not difficult to verify that this will indeed satisfy the axioms to be a near vector space itself or a subspace. And this will be called the subspace spanned by S. So that's the definition. And here are some basic lemmas that weren't difficult to prove. So let VA be a near vector space. Then for all V in V, we will have that span of V will be one-dimensional if and only if the quasi-kernel is the whole of V. So we know that normally for vector spaces, whenever you take a span of a single vector, you will get a one-dimensional subspace. And this will only be true if we have that the quasi-kernel is the whole space. So the next question was, what happens if we move outside of the quasi-kernel? And it wasn't difficult to show then that the span would never be one-dimensional. And so we sat with this very strange question and we asked, is it possible in some near vector spaces to have that a single element can actually generate the whole space? And the answer is yes. And so we have the definition, which looks very weird even to write down. But if we have a near vector space and we can find a V in V such that span V is the whole of V, then V will be called a generator of V. So this is work that was done with Sulgu, and we have a paper on it. And the example that he first discovered of a generator was an example of copies of a near field over itself. But this is a much simpler example to share with you and pique your interest. So let's again look at the same example we did before. We take two copies of Z5 and we have this perturbed multiplication. We've already seen what the quasi-kernel looks like. So if we drew a little picture, we've already said this is V, this is the quasi-kernel. And it's not difficult to show that the element 1, 1 is a generator of V, and 1, 1 is an element that would sit outside the quasi-kernel. In fact, we have a result that says that any element that lies outside the quasi-kernel, 0 lies in the quasi-kernel, but any element outside, so any non-zero element outside the quasi-kernel will generate the whole of V. So why is that interesting to us? Well, that's interesting because there's a whole branch of mathematics that studies dependence and independence called matroid theory. So this means that with near vector spaces, in examples like this where we do have generators, the matroid theory would be different from vector spaces. So there's some very interesting examples that can be discovered. And that is work that I'm currently involved in with Professor Nancy Newdauer from Pacific State University. So next, I thought it would be nice to share with you why I think this matters. So this is a dream of why I think it would matter. I don't have all the pieces in place yet to tell you it does matter, but this is why I think near-vector spaces will be important. So this is a very simple example of a finite linear game. So if you look at an introductory linear algebra book, they normally have somewhere in the application sections a small discussion about finite linear games with some examples to get first-year students interested in the linear algebra. So this particular finite linear game I'm going to present to you comes from the book by Poole. So a finite linear game is a problem that involves a physical system with only a finite number of states, which can be altered by applying certain processes and resulting in a finite number of outcomes. So these type of systems are very prominent in computer science, but I've also had some contact with physicists, and they have indicated that these could be of interest for them as well. So we generalize the idea here, and for the discussion here, I'm going to just look at ZP cases where we have finite states over ZP for P prime. So here's a game that we're going to play. We're going to take some light bulbs, and we're going to take M of them, and they're going to have P possible states, and there's going to be a switch associated with each light bulb. We can represent the configuration of the system at any time by a vector. So V will represent what state the system is in. And we're also going to distinguish between our initial configuration and our final configuration. So the initial configuration being in which state our system starts in, and the final configuration is the one that we're going to ask, can we get to this final configuration by pressing our switches in a certain order, a certain number of ways. So continuing with the setup, for each switch, we are going to have a vector that captures the state change it brings about each light bulb. Each light bulb changes sequentially, so it goes from state 0 to state 1 to state 2, all the way up to state P minus 1. So you could assign, say, state 1 to be a color like blue, 2 could be red, etc. And if we look at our system and how we've set it up, then each change brought about by a switch corresponds to a vector sum. So what this means is that the change brought about after pressing a switch for some I starting with an initial configuration of Ti results in a final configuration TF. So vector addition captures the change that occurs after we have pressed a particular switch. This extends so that the final configuration after pressing the switches in some order is of the form TF. So our final configuration will be our initial configuration plus some scalar multiples of all the switches, and the scalars capture the number of times each switch was pressed. So as a result of how we set it up, we have a vector space, and our vector space consists of M copies of ZP. The vectors are the switches and configuration, and as we've discussed, the vector addition captures the change from one state to another, and scalar multiplication captures the number of times we have pressed each switch. So I tried to draw a little picture here. So here's an example. So we have a row of 4 lights. So there are my 4 lights. And each light can have 5 possible states. So for fun, I assign colors. So 0 would be off, 1 would be blue, 2 red, 3 green, and 4 pink. I chose pink because you don't often see pink in a mathematics talk, so I thought I'll bring some pink in. And here's an example of some switches. So I've picked 4 of them. A is the vector 1, 0, 0, 4. So this means that A would take the first light to state 1. What color was that? That would be blue. It would do nothing to the state of B, nothing to the state of C, so it would leave them unchanged. And then it would take light D to pink. B, for example, would take A to whatever the next state is. It would take B 2 states on, C 4 states on, and it would leave D unchanged, etc. So we've got 4 switches. So in our example, since we have 5 possible states, we are working over Z5, and you can play around with this, but an easy way to start is by taking all the lights off when you start this experiment. So let's make the initial configuration, all the lights off. So there's our initial configuration vector. And we could now ask, is it possible to obtain a final configuration of T? And what would be the interpretation of T? It would be, is it possible to press those switches a certain number of times, one after the other, in such a way that the first light would be blue, the second would be green, the third blue, and the fourth green. And this then translates into a very nice first-year linear algebra problem with a system of linear equations that we can solve. In this case, the coefficient matrix is invertible, and we will obtain the final configuration by pressing switch A twice, switch B 4 times, and leaving switch C and D unpressed. By playing around with this, you'll see not all final configurations will be possible. So not all of these problems would be solvable. But then we know that there are cases where we would not be able to get a final configuration, depending on which configuration we started off with. Right, so how is this related to near-vector spaces? So whenever you have a problem where there's a vector space, it's very natural to ask, what happens if we replace the vector space by something that's less linear? So here's a very simple example. Let's take exactly the same system, but we change what happens when we press a switch multiple times. So you can see as an example, press there. Let's suppose that alpha k was alpha to the 3 times k1, alpha to the 3 k2, alpha to the 3 k3, and alpha to the 3 k4, where k1, k2, k3, and k4 are the normal entries that capture what the switch does. So this becomes a near vector space problem then. And what we have seen is that the theory that we have of near vector spaces so far, relating to the irregularity properties of the quasi-kernel, allows us to predict what the outcome would be in those non-linear systems. So this is work that is collaborative work with Sorgus Anon and Leandro Buenzai, who's a physicist who was at Stellenbosch University and still in and out visiting us from time to time. So as I've mentioned, the structure above with this perturbed multiplication is a near vector space. So what I have illustrated with a very simple example is that near vector spaces give us a way of capturing the behavior of nonlinear finite systems. And if we think about real world systems, the majority of systems are nonlinear. So my big dream for near vector spaces is that in the future, when I give a talk like this, I'll be able to report on some very practical application of this nonlinear behavior to some interesting system. But I'm not quite there yet. It's a dream I won't give up on. But hopefully we'll have our first application either in physics or in computer science in future. Right, so that's the first part of my talk. The second part, which is again related to trying to convince you of the weird and wonderfulness of near vector spaces, I thought I'll share a little bit of my journey of studying near vector spaces so far, just to convince you of not only their importance, but that there's a lot that still can be done. So I started studying near vector spaces as part of my PhD thesis. And normally after a PhD thesis, you're encouraged to branch out and to try and create a niche for yourself. And when I started out, a lot of people didn't have a lot of faith in near vector spaces and how much I could possibly get out of this area. But I'm very excited to tell you that it's been a very beautiful journey and that it's still unfolding. So where I started just studying the algebra, through the most recent work that we've done, I have worked with specialists in matroid theory, which is something I'm really excited about. There is scope for work to be done in graph theory. So there are many applications in graph theory where they look at how a graph can capture a certain algebraic property. And this is work that I've started with a colleague at Stellenbosch University, Dr. Leslie Wessels, who recently finished her PhD. And in her thesis, she introduced some graphs that capture some of the properties that we're interested in of a Nearvector space. I've already mentioned that the matroid theory looks at independence and dependence for different types of structures. And that is work that I'm looking at with Professor Nancy Newdow. So there's some interesting matroids that we would not have for vector spaces that have come out. And then possibly the arrow that I'm most excited about at the moment, and it also links to both the graph theory and the matroid theory, is incidence geometry. So about 1.5 years ago, my master student Jacques Rabi discovered some papers of Andre that are written in English. So Andre is German, and since I don't understand much German, it's been quite restrictive. We've had some papers translated, but we were very excited to find some papers that were in English. And in these papers, he actually describes his thinking of how he defined near-vector spaces and their importance in geometry. So they turn out to be near-affine spaces. And these are papers that I'm very excited about, and they've opened several new avenues of exploration. And whatever we now discover with regards to the incidence geometry will also feed into matroid theory. So there's a large component of matroid theory that looks at dependence and independence from a geometric perspective, so it will feed into that. But also within the geometry, graph theory is often used again to depict whatever the relation is with regards to dependence and independence. So it feeds very nicely into those fields. So that's all I wanted to share for today.
Thanks a lot, Karin. I think that was very clear. I think we all learned a lot about near-vector spaces there, the nitty-gritty definitions and that, but also this last part about the bigger picture, I think is very helpful. So thanks so much for your talk, and I invite everyone to give Karin a round of applause.
Thank you.
And now we have time for questions. I'm sure Karin would be very happy to answer some questions. If I can ask the very first question, yeah, I was going to ask, just to go back to this first slide, the quasi-kernel. Okay.
Yes.
Okay, so it's kind of like the smallest set where as you say, where the rules do hold.
Yes.
Or the biggest set where the rules do hold.
Yes, exactly, the biggest set.
Okay. Okay, we've got Andrew Craig has raised his hand. Andrew, you can go ahead.
Hi, thanks. I was just interested when people are studying congruence lattices of finite algebras, vector spaces play quite an important role because they give lots of nice examples. Is there a notion of a congruence here in a near vector space?
No, so that hasn't been done. That's certainly something that can be looked at.
Yeah, I mean, I'm not even sure if it makes sense. You know, yeah, if it would be easy. I mean, what are the homomorphisms between near vector spaces? Is there an idea of a homomorphism?
Yes, there is, and in fact, so I also should have mentioned. So maybe if I go down to my sketch, something I omitted that's important. There should be another arrow here. So this is also work that's being explored, and it's linked to what you've mentioned. Is that I'm also involved in a project with Zurab Yanalitsa, we're looking at the category theory, and we've got a master's student who's actually looking at the categorical aspects. And of course, the homomorphisms are central to that and understanding them. So that's a project that is active at the moment. Homomorphisms have not been studied much yet, and that's part of this project. So I imagine once we have that in place, then certainly it opens up for the type of questions that you've raised as well. I think it'd be interesting. Thank you. Bruce, I don't know if there are any other questions.
I have a question.
Hi, David, you can ask it.
Yes, thank you. There is a notion of nearing modules. And when I heard about near vector spaces, what came to my mind is that perhaps it's that notion, but for which the ring on which a module is defined is perhaps a field, something like that. Do you think there is a link between what you described here as a near vector space and the one I've been talking about?
So viewing it as a module.
You see, ordinarily, when you talk about a vector space, it is just
Yes.
over a field.
Yes.
And given that there is already a notion of nearing modules, what came to my mind when I saw the topic was that perhaps here you are taking your ring to be a sort of a field. And I'm asking whether, I realize from the definition that's not what it is, but I'm wondering whether there is a link between what you describe as near vector spaces and the nearing modules.
Yes, so there is a link. Firstly, if I go back to my slides, so what you've described is exactly what informed the, sorry, now I can't for some reason, sorry, my laptop I think is frozen up. But if we go right back to the beginning where I spoke of the different definitions. So there's a definition by Badelman, that's the one I spoke about that Prudence Jagba worked on. And his near vector space is actually defined as copies of nearing modules. So he went starting off with that as the definition. With regards to Andre's near vector spaces, yes, there is some notion it's related to near fields. So there's a result by Andries van der Walt, which I didn't mention in my talk, but he was a mathematician at Stellenbosch University many years ago. And in one of his papers, he characterizes every finite dimensional near vector space as being copies of a near field with certain automorphisms defining the multiplication. So yes, there is a link.
We've got a question from Iochukwu in the chat.
So I'm just trying to find my way to the chat.
He says, hi, Karin, thanks for the nice talk. Could you say a bit more about the connection of your work with incidence geometry?
Yes, so I'm actually going to do more than that. I'm going to ask my student Jacques Rabi if at some point very soon in the future he's available to come and talk to the seminar and discuss his work. But just to say that in the papers by Andre, he shows that the near vector spaces are examples of near field spaces, and a near field space is a near affine space. So if you know a bit about incidence geometry, you'll know about affine spaces. So a near affine space is an affine space, but again with a little less linearity. And Andre's work was studying the near affine spaces and seeing what properties those geometries would have. And there's only 2 papers on this topic, and Jacques Rabi has added quite a lot to this topic already as part of his master studies. So I think it would be nice in future to follow up this talk with a talk by him describing his work.
Okay, thanks for that. And yeah, and we've got a question from Leon.
So I can't hear anything. Did you ask something?
He might have been muted.
Sorry, I was muted. Sorry.
Hi, Leon.
Hello, Karen. Yeah, so it's not a question. It's maybe just a remark for the other participants. Karen mentioned Andries van der Walt, and Karen is Andries van der Walt's mathematical granddaughter.
I am.
Thank you.
Yeah, so my supervisor, Johan Meyer, studied under Andries van der Walt. So yes, proudly his granddaughter.
Okay, are there any further questions? Comments?
I hear someone typing. Sounds like a lengthy question. Getting quite nervous.
Okay, maybe someone's typing an email. Okay, so then I think I'm gonna, yeah. Zabine has just said in the chat, thank you, Dr. Karin, for a nice presentation. Have you practically implemented these concepts of switching on-off thing in reality?
Yeah, well, not yet. It's a project that's still under investigation. We're still busy with it. So no, not yet. But I'm looking at it in computer science. So I have someone I'm working with there. And then I'm also working with someone in physics. COVID changed a lot for us, but it's still the dream. And I'm still going to continue with those investigations.